In this video, I want to talk about how you can process a directed graph to solve an algorithms question. So to start, let's talk about what a directed graph is. What's unique about a directed graph is that all of the edges have a specific direction. Let's look at the example edge here called A. You can see that it's an arrow. So what this is saying is you can go from the 0 node to the 1 node, but you cannot go from the 1 node to the 0 node. So if you think of the example we discussed in the last video, where our nodes represent cities and our edges represents roads between these cities, then a directed edge is basically a one-way street, right? You can travel from 0 to 1, but you cannot travel from 1 to 0. I did want to include an example here to show you that it is possible to have a two-way street with a directed graph. The only difference is that is now represented by two edges. Edge B is telling us that we can go from node 0 to node 2, and edge C is telling us that we can go from node 2 to node 0. So we can have two-way streets, but you need two edges to represent them. Now, the next thing I want to talk about is how we represent an edge, because it's slightly different in a directed graph. Previously, we saw that when we're representing an edge, we represent it by the start and end point. In the last video, I said the order doesn't really matter. We could have flipped them around. That is no longer the case here. So let's focus on this A edge here. Let's say we wanted to diagram out just this A edge. Previously, the way I said we would do it is we just put the start and end point. So I said it could be either 0, 1, or it could be 1, 0. But the way we're going to define directed edges is going to be that the initial element is going to be what we'll call the start, and we'll call this element, the last element, the end. Meaning this edge A represents the fact that we can start at node 0 and end up at node 1. In this case, we would be saying that we can start at node 1 and end at node 0. That is not true. You cannot go from the 1 node to the 0 node. So this is invalid. When we're talking about a directed graph, the order does matter. You typically will want to put the start node first and then the end node. Obviously, it could be flipped. It really doesn't matter. You can represent, when I say it can be flipped, I mean that you can put the end, like you can define it so that you're doing something like this, where you have end, comma, start. And in that case, 1, 0 is how you would represent this edge. It typically will vary, and they will specify whether index 0 of your array represents the start or the end in the problem itself. For our purposes, we are going to assume that index 0 is the start and index 1 is the end. So we can go ahead and erase this. This is not useful for us. It is incorrect. Okay, so now we understand how we're representing an edge in our directed graph, and we understand the concept of a directed graph. So I want to break down the input format. It's very similar to what we discussed in the last video, but I want to go through it nonetheless. You can see the input format up here. We have this 2D array that is effectively the exact same thing as the graph that I've drawn on the left. So you can see that the edge A is modeled here. We have 0, 1 as a directed edge. We have edge B, which goes from node 0 to node 2, and that's modeled right here, and that sort of continues onward. I've labeled all of the edges in the graph and labeled them the same way in the input so that you can match between the two and understand, which pair on the right corresponds to which edge on the left. Now, let's say we were trying to do any sort of standard graph traversal problem. So to keep things simple, let's say we wanted to find the shortest path from node 0 to node 5. Or to make this more concrete, let's say we're going with the example of cities and roads. So we want to find the shortest path from city 0 to city 5. Now, what we discussed in the last video is that what we care about at a particular node is all of the nodes that we can reach from this current node. So as an example, when we're on the 0 node, we want to be able to we want to know that, hey, we can go to the 1 node or we can go to the 2 node. Those are our only two options when we're at the 0 node. And we determined that we can do this with a hash map. So what I want to do is I want to actually build out this hash map, and I want to do it not just arbitrarily as a human looking at this visual, but I want to do it based on this input here and see if we can start to understand some sort of pattern or consistent logic for how we are building out our hash map given an input, because I think that'll be really helpful in future problems. So, let's see. Okay, so what we want to do is we kind of want to go one edge at a time, right? Because that's what we have. We have a giant array that contains a bunch of edges. And remember, the way this graph works is we want to say that for a particular node, we want to map to an array that contains every node that we can reach from our current node. So from the 0 node, there's an edge that takes us to node 1, and there's an edge that takes us to node 2. So we would represent it like so in our hash map. So programmatically, let's focus in on this very initial edge right now, this 0, 1 edge. What does this really represent? Well, we know that this is the start point and this is the end point. So what we're saying here is we can go from node 0 to node 1. So if we think about that in the way I was diagramming it here, well, that means we can go from node 0 to node 1. So we can represent that by putting 0 as a key in our graph, and we can say, all right, that's going to map to potentially several different values. So we'll keep an open array here, and we'll say we can go to 1 from 0. That's all of the information that is contained by this initial edge, right? Because we can't go from 1 to 0. All we know is we can do this transformation here. Okay, great. So now we can move on to the next edge. At this edge, what information do we have? Well, this is telling us that we can start at the 0 node and end up at the 2 node based on the same concept, right? This is our start node, this is our end node. So we can map that. We can say, all right, when we're at the 0 node, well, we can also end up at the 2 node. So we want to add another element here that says 2. And that's all the information that edge B is telling us here. And we can continue on to edge C right here. So what this is telling us is that we can start at node 2 and end at node 0. This is a bit interesting. So remember, this is the reverse of when we went from 0 to 2. So what we'll do is we'll come down in our hash map and we'll say, all right, let's add an entry for 2. You can notice I'm leaving a space because we may want to fill in something there later. But all we're going to do is we're going to come here and say, all right, let's create an array. And we know that if we're starting at 2, which is what this key represents, we can end up at the 0 node. And the reason I'm not closing these arrays is because we don't really know if we're going to be adding more numbers there. So I'm just going to keep it like that for now. So this edge has been completed. You know what? I'm going to go ahead and check off the edges we complete as we do it. So we've completed these 3 now. Next, we're on this edge that starts at the 1 node and goes to the 3 node. So we're going to come in here and we're going to realize, hey, we don't have any key for 1. So let's add another key. And we'll say, all right, from 1, we can go to the 3 node. And that's all the information we get from here. Now, we hit this edge, E. This is telling us that starting from the 1 node, we can go to the 4 node. So we come to the 1 node, we add this value here that says, hey, we can get to the 4 node. And we can check that off. That's all the information we have there. On the F edge, it's telling us that we can start at node 3 and end up at node 5. So let's go here. Let's say, all right, if we're at node 3, then we can go to the 5 node. And that's all the information we can get from F. Lastly, if we look at G, this is telling us that if we start at the 4 node, we can end up at the 5 node. So let's come here and add an entry for the 4 node and say that we can reach the 5 node. That's all the information from G, so we can go ahead and check this off. I will close all of our arrays now, because now we know we're not adding anything more. And this is a hash map representation of the directed graph that we have on the left. There is one point I want to make, which is that if you look at all the nodes in the graph, one of them is not present in our hash map over here, which is node 5. And this is an important point, which is that you can choose to represent the 5 node here and say that its value is just an empty array, because there's nothing that you can reach when you're at the 5 node. You have nowhere to go, because you can't go backwards against these edges, and there are no edges coming out of 5. Or you can also just choose to not represent 5 at all in your hash map. It kind of depends on the problem. In a lot of problems, you won't really need to interact with any node who has no children. So in those problems, you can just leave it off. But in some problems, you may want to include the 5 node. So it's something to be aware of when you're working through these kinds of problems. Now, the last thing I want to talk about is the time and space complexity of our solution. So over here, we can write complexity, and it's actually going to change based on that variable that I just identified right there. So there are kind of 2 scenarios. There is number 1, which is going to be this, and there's number 2, which we'll write out down here. So in number 1, this is the scenario here where we left off the 5 node, right? So if a node is not present as the starting point of an edge, we don't need to worry about it. In that case, we can write it under here. We can write our time is going to be O of, we left off that node, so that's going to be O of E, and the space is also going to be O of E. Now what is E? E is going to equal the number of edges in the graph. Now let's talk about why that's the case. It's actually not too difficult to see, because if you think about the work we did, we just iterated over these different edges here. So we're at the best case scenario, we have to iterate through every single edge. That's just what we are doing. So it can't be anything lower than O of E. And you can imagine if we had maybe, I don't know, like 100 nodes, not that many nodes, only 100, but tons of edges between all these different nodes, then we would still be doing a ton of work, right? Because we would be iterating through this gigantic array, even though it's only 100 nodes. So you can see that in that scenario, the E is really determining what happens. It's possible that a lot of nodes get left out, like this 5 node here. So the number of nodes doesn't actually end up mattering too much. But the alternative scenario, which is number 2, is what happens if we did include the 5 node down here? Well, in that case, things will change a little bit. Oops. So we'll have our time and we'll have space, and we're going to define one more variable. We're going to say V is equal to the number of vertices in a graph. And I want to define what a vertex is in a graph. It's actually just another name for a node. So we have this 0 node, that's a vertex. This 2 node, that's a vertex, and so on. And so the time complexity here is actually going to be O of V plus E. And similarly, the space complexity here will be O of V plus E. So the E part is the same as before, right? We have to iterate through these edges in the worst case to produce it, even if we were including some sort of value like this at the end of our hash map. But the difference is this. You can imagine that if we had 0 edges, but maybe 500 million nodes, well, we would still create 500 million entries in our hash map. They would just all look like this one where it's an empty array. But you can see that the number of nodes is still affecting the amount of work that we do. So that's why we also have to include the number of vertices here. So if the number of vertices or nodes is very, very high, this will take a long time. If the number of edges is high, it will also take a long time. And similarly, you can note that we are storing one entry for every single edge, right? From 0 to 1, that's a single edge. And one entry for every single vertex. As an example, we have this 5 vertex right here. Okay, so that covers the time and space complexity of this process of basically manipulating a directed graph as a 2D array into a hash map that you can deal with. Now, I want to jump into the implementation so we can get a sense for what this looks like in code. Now, let's see how to process a directed graph in JavaScript. I've copied the example input that we just went over here as a 2D array, and our output is going to be a hash map, so in JavaScript, an object, where we map each node to an array that contains all of the nodes that you can reach from that node. So before we get into the solution, let's start by defining our test. So let's just grab the input here. Let's assume our function is already working. So let's say we have a function called process directed graph. That doesn't exist yet, but we're going to write it in a moment. And then let's just console.log our graph to see what it looks like. Okay, so now let's define our function that we'll call process directed graph. It's going to take input as a parameter, which is going to be this style of 2D array. And now let's think. What did we do in the approach? We basically iterated over every edge in this input and inserted it into our hash map, or in JavaScript, our object. I'm going to start saying object from now on since we're working within JavaScript. So let's start by creating our graph, which will just be an empty object. And we know in the end we want to return our graph because that's all this function is supposed to do. So now what we need to do is iterate through every single one of these edges. So what we can do is just use the for each method in JavaScript. So we can say input, which is our 2D array, dot for each. And then here we're going to pass a callback function. So let's say given an edge, we want to do something. So an edge looks something like 0, 1. And the very first thing I want to do is grab out the start and the end. So what we can do is we can use some destructuring here. And we're going to grab the start and the end from edge. So all this is saying is if we have 0, 1 as the current edge, then set the variable start to be 0 and set the variable end to be 1. Here it would set start to 0, end to 2. We could have destructured in here. I just think it'll be a little bit clearer this way in case anyone's not familiar with the destructuring syntax. It might be overwhelming to put it in there. Okay, so now we have our start and end for, let's just focus on the initial pair. So we have 0 as our start and 1 as our end. Now what did we do in our object here? Well, we said at the key of 0, I want to add 1 as a potential value. But right now, there is no even array here. So if we tried to go to like graph at 0, that's meaningless. That's just undefined. There's nothing there. So what we want to do is set it to an empty array if it doesn't already exist. So we can say if, and we want to check if the key is not in the graph. So the easiest way we can do that is we can say if graph at start, yeah, because we want to have 0, we want to go to 0. If this is falsy, right? So if this was undefined, then we flip it and this condition becomes true. Then we just want to say, hey, graph at start should just be an empty array. Otherwise, we don't have to do anything there. So now we know that we either just created an empty array for this position or we have one from before. Now, all we want to do for this edge here is we want to say add at the key of 0, just add 1 as a value. So we want to say, go to our start. Now this whole thing is going to be an array. And then in that array, we want to push the end. So that's saying, take our start, which is 0, go to the value in our hash map that corresponds to it. So this, and then just push a 1. So we're adding a 1 to it. And when we get to the next position, where we're at 0, 2, we're going to say, all right, go to the value for 0, which is going to be this array here, and add the 2. And you can see that this process would sort of continue onwards. This covers the essential idea of how we're building our graph. All we're really doing is iterating through our edges and then inserting values into our hash map. So let's go ahead. Oh, I just saved that, and I have a linter that just reformatted this, but it's the same as before. And let's go ahead and test this to make sure it works, and then we can move on to one other thing I want to cover. So let's see. So we have 0, that gives us 1, 2. 1 gives us 3, 4. Is that correct? Yep, and then 2 should be 0, and then 5, 5. Let's make sure. So 2, 0, 3 is 5, 4 is 5. Okay, great. So it looks like that's working. The other thing I want to cover, or actually, hold on. Let's do the time complexity of this and the space complexity of this, and then we will talk about the other option. So here, our time complexity is going to be O of E, and our space complexity is going to be O of E. That is pretty straightforward to see, I think, from the code. Right? Obviously, these two lines of code here are constant time and constant space. Really what ends up mattering is this section here. In terms of time, everything we're doing at each iteration is constant time. So the key is how many iterations are there? Well, we're going through every edge in the input, so it's O of the number of edges. Let's define that here. E is number of edges. In terms of space, you can imagine that, for every single edge that exists, we are putting a pair, right? Like when we have 0 and 1 like this, that represents a particular edge. So we could have tons of space used based on the number of edges that we have. So that's the time and space complexity for this solution. The other case I want to handle is this part, right? We said that sometimes we might want to include a node who has an empty array, meaning it has no other nodes that you can access from that node. And in that case, when that happens in a problem, this will actually look a little bit different. Usually you're going to get a value that's going to be something like n. And so here we'll have n and input as passed as arguments. And then up here we can say, hey, we also have a value n. And let's delete this. This is no longer going to apply, at least this complexity part. N is just supposed to be the number of nodes that you have in your graph. So you can see that we have 6 nodes because we go 0, 1, 2, 3, 4, and 5. So that's a total of 6 nodes, 0 through 5. And what you're going to want to do is you're going to iterate through every value that is valid. So 0 through n minus 1, right? Because in our case, n of 6, and we had 0 through 5 as our nodes. And yeah, so let's actually set that up real quick. So we'll say let I equal 0 as long as I is less than n, I plus plus. And what do we want to do at every single one of these iterations? Well, we just want to say graph I equals an empty array. That way, even though this 5 is never going to be the starting point of an edge, we still set its value to be an empty array. One thing that's nice about doing it this way is now we can delete this line of code, because this should never happen, right? Every node should already be initialized to an empty array. So we can delete this here. And this solution should work as well. I believe that's all. We have n. We're saying iterate through n, set empty array. Okay, this should work. Let's go ahead and test that this works. So you see we have 0 has 1, 2. This is the same as before. 1 has 3, 4, same as before. 2 has 0, same as before. 3 has 5, same as before. 4 has 5, same as before. And then we have this piece where we have 5, which gives us an empty array. So we've been able to solve that piece. Now the complexity here is also, I think, easier to see in the code. The time is going to be O of V plus E, and the space is going to be O of V plus E. Now this part is O of V. Let's define what V is actually. Let's say V is equal to number of vertices. So this part here is saying iterate through every node or every vertex in our graph, because they're telling us that there are n nodes. You could also put n instead of v here. It doesn't particularly matter. This is just more of a convention. So here we're saying we are iterating through every single vertex. So we don't even care how many edges there are. It's at least going to be O of v. But we're also iterating over every edge. So if the number of vertices is gigantic and we only have like one edge, we still have a very high time. If we only have a small number of vertices, maybe 100, but we have like 500 million edges or some very, very large number, That's still going to take a long time. So you can see that both V and E play into our overall complexity. In terms of the space, it's a very similar thing, which is that if we had a ton of vertices and no edges, well, we're still storing one entry for every single one of those vertices. So the V is an important component of our space complexity. But the other side is important too, because remember, for every edge, we have a pair. Like this 0, 1 pair here represents a particular edge. So we're also storing some sort of information for every single edge, so that matters for our space complexity as well. That's pretty much it for how we process a directed graph. So there are two approaches. One, where you only consider nodes that appear in your edges, and that has O of E time, where E is the number of edges. And approach number two, make sure that every single node from your graph is included. This one runs in O of V plus E time and space. That's it for this video, and I'll see you in the next one.